Floor is yours, Arno.
Thank you. So good afternoon, good evening, good morning. My name is Arno Pärssinen and I will be sharing this keynote session today. And I would like to introduce our keynote speaker, Professor Mark Rodwell. Mark Rodwell holds the DeLuca Family Endowed Chair in Electrical and Computer Engineering at University of California, Santa Barbara, and directs the SRC DARPA ComCenter Wireless Research Center. His research group develops high-frequency transistors, ICs, and communication systems. Professor Rodwell's keynote today is entitled as 100 to 300 gigahertz wireless communications, IC and system design. Professor Rodwell, please.
Thank you so much for inviting me. It's a pleasure to be here and to be represented, and I look forward to the whole conference. Thank you. Thank you for the introduction. So I'm Mark Rodwell from the University of California, Santa Barbara, and I thank you for your invitation. And I'm going to be talking about 100 to 300 gigahertz wireless communications, specifically IC and system design. I'd like to acknowledge the support of the Semiconductor Research Corporation and DARPA for our center, and I would like to acknowledge the work of the many collaborators I have in the center in the area of system design, IC design, and high-frequency transistors. I would also like to acknowledge specifically the SRC sponsors, including these many companies that you see right here. Okay, why are we working on 100 to 300 gigahertz wireless? Well, as we all know, wireless networks are seeing exploding demand, and the immediate response to this has been to move to 5G carrier frequencies, where this is spanning the range from roughly 10 to roughly 100 gigahertz. Most of the activity at the lower frequency range, so perhaps we should call this 5G and this maybe 5.5G. But at any rate, in moving to higher carrier frequencies, we're bringing in increased available spectrum, and because the wavelengths are short, extensive beamforming. More on that in a moment. The next generation, which perhaps we might call 6G, possibly might use carrier frequencies even above 100 gigahertz. Why? Because this would bring further massive increases in the available spectrum, and in combination, the use of massive spatial multiplexing. In combination, we can have both backhaul links and endpoint links to mobile users using spatial multiplexing and provide terabit per second capacities. And in imaging radar, we can have compact systems to put on a car or a drone that provide high angular resolution so that we can see small things far away. Okay, why are we moving to short wavelengths? Well, first, in going to short wavelengths, high frequencies to repeat, there's more available spectrum. But that's not the only benefit. In a phased array of a given size, if we're going to steer over 180 degrees, the element spacing is roughly half a wavelength. So higher frequencies means in an array of given size, we can have more elements. And at least on paper, we can support as many simultaneous independent signal beams as the number of array elements. So we can use that to produce many independent signal beams and reuse the available allocated radio spectrum over and over again to increase our capacity. We can do this in an endpoint link like I'm showing you here, where we perhaps have 4 arrays, north, south, east, west, on the top of a light or telephone pole, and each one of these is radiating multiple independent signal beams to end users. We can also similarly use that similar spatial multiplexing in a backhaul link to bring signals back to the internet, where we might have a set of transmitters transmitting independent signal beams. And here the receiver has a set of elements that act as a phased array. And if the array is long enough, it has sufficient angular resolution to separately resolve the signals coming from each of these transmitters. When we do that, the number of independent beams we can support in an array of a given length depends on the wavelength. And if we double the frequency, we double the number of channels we support in a linear array. And if the array is square and it has some fixed dimensions, if we double the frequency, we quadruple the number of channels we can support. So there's the possibility of truly phenomenal transmission capacities when we do this. In radar imaging systems, of course, the angular resolution is proportional to the ratio of wavelength to aperture length. So an array of a given size, a shorter wavelength implies a greater angular resolution and more pixels in our image so that we can ultimately move to a TV-like image one day with an advanced radar system. But against this, we have high losses at high frequencies in foul or even humid weather. The frisk path loss, lambda squared over r squared, is of course higher. At any moment in time, integrated circuit technology is poorer at higher frequencies. We have less output power from our power amps and higher noise figures from our receivers. And at short wavelengths, the beams are easily blocked. So as a consequence, at these high frequencies, we can conceive with fairly conservative assumptions that we can build even terabit aggregate capacity wireless links, but they're going to be short range and they're going to have significant intermittency, and the systems have to be designed to hide that from the end users. So let's look at the applications. We're looking in our center at several applications, and I've sketched them out here. A Mimo hub or base station transmitting multiple independent signal beams to multiple mobile users, as I'm showing here. We're focusing that at 140 gigahertz. A backhaul link, we're working on a Mimo backhaul link, again, spatially multiplexed in the manner I've described, and we're focusing on 210 and 280 gigahertz on this. And we're further behind on the imaging radar system simply because the number of hardware channels we've got to build is large and a bit overwhelming us, but we're also, at least on paper, hoping to use similar hardware to build imaging radar systems at 140 or 210 gigahertz. So let's look at the first of those. This is a 140 gigahertz massive Mimo hub. Let's take a look at the link budget. We've got a telephone pole again or light pole with 4 array faces on it. Each one might have 256 elements. If we assume that array has 256 elements, is talking to 128 users, if we assume that the power amplifiers each put out 21 dBm and the receivers have 8 dB noise figure, if we assume that the receivers handsets are 8x8 arrays, which are about a centimeter by a centimeter, and the receiver noise figure is about 8 dB, then if we assume either 1 or 10 gigabits per second per user, then we can support either 230 meters range at 1 gigabits or 100 meters range at 10 gigabits per second, even if it's raining at 50 millimeters per hour, and even if we give ourselves 17 dB total safety margins for things like aging, design margins, end of life, and just conservative system design so that the customer is always happy. So these numbers are well within the state of the art. And so this system with something like 128 beams per array face with 4 faces, supporting 500 users at 10 gigabits per second per beam, that's 5 terabit per second aggregate capacity. And from a link budget point of view, that's feasible. Well, why use 140 gigahertz? Why not use 70 gigahertz? If we use 70 gigahertz and kept the same size array in the base station, keep the same number of elements in the base station in the handset, then the range increases to 168 meters. But more likely, it's not acceptable to increase the physical size of the array in the handset. If we keep that at a constant 8x8 millimeters, then the link budget is back to the same overall transmission range, whether it's 70 gigahertz or 140 gigahertz. The simple point being that the bandwidth we would need to support this high 10 gigabit per second data rate, about 5 gigahertz, is more likely from a regulatory standpoint to be easily obtained around 140 gigahertz than it is around 75 gigahertz because it's a smaller fractional bandwidth. If we considered the same hardware, but producing not a 256 element array, but an 832 element array, then the either 1 or 10 gigabits per second per beam would be able to support a shorter distance of about 70 meters at 1 gigabit per second or 40 meters at 10 gigabits per second. But Although the range goes down, if you consider the total number of array modules that you're using, the same number of array modules will cover the same number of users and will serve the same area on the ground, whether we build a large number of arrays, each with, say, 32 elements, or a smaller number of arrays, as I've mentioned to you here, of 256 elements. And this is perhaps a more reasonable system design. Now let's move on to the backhaul application. Let's look at the case of backhaul using 210 gigahertz. If we have an 8-element array of transmitters and each is transmitting 80 gigabits per second, let's assume that each element in the transmitter is a 4x4 subarray. That'll give us a large enough aperture to be directional so that we get the necessary link budget. And with an array there, we can do a little bit of beam steering so that we don't have to mechanically align it too precisely. So we have an 8-element transmitter, we have an 8-element receiver. Each one of these is a 16-element subarray. If we're operating over half a kilometer range at 210 gigahertz to make the angular resolution work out, the overall baseline is about 3 meters, or in other words, about 10 feet. 8 elements at 80 gigabits per second is giving us an aggregate capacity of 640 gigabits per second. Again, that's a phenomenally large number. Is it unrealistic to think that the hardware can do this? Well, we're looking to get 500 meters range, and to do so in 50 millimeter per hour range, which gives us about 20 dB per kilometer attenuation. We'd like to give ourselves about 20 dB conservative safety margins. And if we do that and work out an elementary link budget, if the receivers have about 6 dB noise figure, then each power amplifier needs to radiate about 18 dBm, about 70 milliwatts or so. So again, this is within the state of the art, at least in terms of transmitter and receiver hardware. And so we should be able to build such a system. Again, why look at 210 gigahertz? Why not a lower frequency? But before I even ask that question, what about a linear array versus a square array? In the linear array, as I gave you the numbers a moment ago for the required transmit power, if I multiply that by the number of elements, we're radiating a total of about 3 watts. If we go to a 64-element array, there are 8 times as many channels, and the capacity goes up 8 to 1 to 5 terabits per second on the same half a kilometer link. When we work out the link budget, we're still only radiating a total of 3 watts, even though there are more elements. In other words, the output power per element is going down. Why is that? And the answer is because the overall arrays have larger area, so there's greater aperture directivity helping the link budget. So again, this looks feasible from a point of view of hardware performance, but if you've been counting, there's very, very large numbers of transmit and receiver channels here. And the main question is, this is a complex system. Can we build it cheaply? Now let's move quickly to the question of why go up to such a high frequency? Why not do this at 70 gigahertz instead of at 200 gigahertz? Well, if we build an 8-element linear array, we would need to radiate a little bit less power, but our array to get the necessary angular resolution now needs to be 5 meters long, which is pretty inconvenient in a linear array and becomes extremely inconvenient if we're looking at a square array. So simply the reason for going to high carrier frequencies in this case is that the spatial multiplexing requires some array length, and that array length is much more reasonable at higher frequencies. So now let's look at the system design of these systems a little bit. The first concern in such massive MIMO systems is, gee, we've got many, many signals, and there's the potential for them to intermodulate due to amplifier nonlinearities, due to phase noise, due to the resolution of the A to D converters. So there's been a lot of work in the systems team, and there are a number of findings. For example, the analog to digital and digital to analog converters. If the individual data streams are QPSK, and if the load factor, meaning the number of signals being transmitted divided by the number of antennas in our system is roughly 1/2, then it turns out that we only need about 3 to 4 bits resolution in the A to Ds and the D to As. These are the scientists in the center who determined this. A simple intuition as to why this is happening is simply, given that there are more RF channels and hence more A to D converters than the number of signals, there is in some sense a hardware oversampling, and that is increasing the effective signal to noise ratio. In a similar fashion, we find that the amplifier 1 dB gain compression points only need to be about 3 to 4 dB above the average signal power level. And so the RF component linearity is not terribly challenging. In a similar way, in analyzing the system, we find that the required phase noise in a massive Mimo system is in fact slightly less challenging than the required phase noise for a single transmitter, single receiver link, having the same symbol rate and the same constellation. A major question is, how do we do the digital beamforming in such a system with so many signals and so many antennas? Surely that's of massive computational complexity and is not physically feasible. The first major contribution to addressing this problem is to understand that the signal is best addressed not in antenna space, but in so-called beam space by forming a spatial fast Fourier transform of the signals coming from the antennas so as to first resolve the incoming signals by their direction. And a spatial fast Fourier transform, as the name suggests, is computationally efficient. Having first separated the users by the direction, additional algorithms by Madov's group and by Studer's group have then found that the business of separating one closely spaced user from another can also be done in a numerically efficient way. Following this work, Christoph Studer's group between Zurich and Cornell will be showing at the ESS-CIRC conference in the very next few days a world record throughput digital beamforming IC for Mimo based on the algorithmic work we've just discussed. In addition, in Mimo arrays or even classic phased arrays, if we're dealing with very high data rate symbol streams in arrays that are also physically very wide, we can run into the problem of the modulation bandwidth of the array being insufficiently large. This is called the true time delay problem. And both Madov, Cabrich's, and Studer's groups have found that this can also be addressed in a computationally efficient way by doing combinations of temporal and spatial fast Fourier transforms of these signals are emanating from the receiver channels. Now let's look briefly at the transistors to build such systems and the choice of technologies. Of course, as IC designers, we can think about CMOS, compound semiconductors like indium phosphide, silicon germanium, or gallium nitride. CMOS is providing good output power and noise up to 150 gigahertz, but the performance is really degrading rapidly above that, and building transceivers much above that frequency, CMOS is not an attractive thing to do for a long-range system. And highly scaled CMOS nodes smaller than about 20 nanometers do not provide improved performance. In fact, the RF performance is degrading with scaling. And technology nodes around about 45 and 32 and 22 nanometers are best. Indium phosphide bipolar transistors are producing record output power and power added efficiency in roughly the 140 to 300 gigahertz range. Silicon germanium is not bad for a power amplifier, it's better than CMOS, not at the level of indium phosphide HBT, and the noise performance is not competitive with either indium phosphide HBT or even CMOS within the frequency range that CMOS works well. Gallium nitride HEMT is providing record output power below 100 gigahertz and up to about 120 gigahertz, and people are working on improving its performance. The world's best low noise amplifiers are being produced by various substrates, but always the channel is an indium gallium arsenide channel in the field effect transistor. And I won't take the time, perhaps you've looked at these graphs so you can look at it online later, but here's a quick technology comparison of noise figure output power and power added efficiency across these technologies. So what does the future bring for these technologies? Well, the gallium nitride transistor technology, as I mentioned, is producing world record by a large margin output power and efficiency below 100 gigahertz. And there are several groups worldwide working to improve this frequency range so that this is a competitive technology well above 100 gigahertz, but the jury is out on that. Indium phosphide bipolars are, the bandwidths of these are about 1 terahertz right now, and these are quite good for efficient power amplifiers in the 100 to 300 gigahertz range. As I mentioned, in-gas channel field effect transistors, these are presently the world's fastest transistors and the world's lowest noise figure, albeit maybe not as manufacturable as you might like. And then several groups worldwide are looking at using high K gate dielectrics to further scale the device to perhaps, if they're successful, to improve the frequency range and the noise figure of these transistors as well. So now let's move along to integrated circuits and packaging technologies, focusing initially on 140 gigahertz. First, let's understand roughly the packaging design problem. And we need to understand that different systems are going to have different physical designs of the transceiver array. If I'm looking at a military application, perhaps an airborne radar system, that radar's got to steer over a wide angular range, probably nearly 180 degrees, and it needs to do so both vertically and horizontally. Now, to do that, the elements in the array need to be roughly half a wavelength spacing in a two-dimensional array. Now, at 140 gigahertz, that corresponds to a 1 millimeter pitch between elements, and it's getting quite hard to fit all of the electronics in the available space between elements. And the heat that's generating is therefore dense, and there's a challenge of getting the heat out, particularly if it's a high power transceiver. We can say, well, you know what, let's have the array here and let's move the integrated circuits and electronics off to the side. But now you've got to run long wires from your array to the integrated circuit. And it depends how big the array is. If the array only has a few elements, you can get away with this. But the two problems you have are the losses of these interconnects. And because these are not skinny wires, but 50 ohm transmission lines, just physically fitting them all in. Against this, we need to understand that not all systems need to steer in both vertically and horizontally. If I am got a base station here, I can steam the beam horizontally to cover most users. If I've got a point-to-point link here, my first impression is I'll use something that's fixed aimed. I don't need any beam steering at all. But maybe the installer has not aimed it perfectly, or the wind is blowing it about a bit, and I'd like a little bit of electronic steering both horizontally and vertically. But in this case, I don't need to steer it over 180 degrees. So if I don't need to steer it over 180 degrees, the element spacing one way or another, there are several ways of doing this, can be made larger. So this is the most difficult problem of a two-dimensional array at half wavelength pitch. You've got the same problem in, say, a cell phone handset, but at least this is radiating less power. So the electronics is simpler and there's less of a heat problem. The base station problem here and the backhaul links, the system is physically easier to design. Let's think again about that base station where we're steering the beam horizontally. Maybe you say, well, gosh, that's no good. We still need a two-dimensional array there because some of the users are in tall buildings high up. And it is true, but I will point out that you can engineer, and this is well known, you can engineer the beam pattern to deal with this even in a one-dimensional array, because if the building has a maximum height, then the closer the building is, although the angle of radiation is getting steeper and steeper, the distance is getting shorter and shorter. And it's a quick bit of math to show that you'll keep the same signal strength for this building as long as the side lobe power is varying as 1/sine² of the angle, which I've sketched here as the side lobes. So if you work that out and say, how much power am I putting into the side lobes and thus not putting into the main beam? Well, it's always, no matter what beam width you're designing for, less than 50%. So to provide these side lobes so that you can always help and illuminate someone in a tall building, you're costing yourself at most, usually less than 3 dB in the amount of power going horizontally. So arguing that we need two-dimensional beam steering to help people in a tall building is perhaps not as strong an argument as we might think. The second question is exactly where are the users that we're trying to talk to? Here's a rectangular array with both elements both distributed horizontally and vertically, a 2D array. Here's a 1D array where the elements are all in a long skinny line. The arrays have the same number of elements, they have the same overall output power, aperture area, so the overall antenna gain and the overall link budget is going to be the same. They have, because the element is the same size, the overall field of regard, the range that you can steer over is the same for the two case, but because the overall areas are different shapes, when we aim a beam, we're aiming a beam of a different shape. And we're dividing the field of view either into long, skinny vertical stripes or into squares? Well, which one's better? And the answer is it depends on the two-dimensional probability spatial distribution of the users. Here I'm looking at two-dimensional array. Here I'm looking at a one-dimensional array. In a one-dimensional array, we're dividing our field of view into skinny vertical stripes. In the two-dimensional array, we're dividing our field of view into rectangles. Well, if the users are distributed uniformly both in this plane, horizontally and vertically, then both of these are getting roughly an equal chance of an equal number of users in each resolution element, and so everything's fine. But that seems kind of unlikely that we've got a lot of people on the ground and an equal number of people up in those buildings looking out of windows. More likely, we've got a lot of people on the ground and a few people up there. And there's an awful lot of resolution elements here which have nobody in them, and we're not using our system capacity well, and we would have been better off breaking our field of view into thin vertical stripes, which is what the horizontal array gives us. I don't claim this is a completely general answer or all of the things we must think of, but simply comment that the spatial distribution of the users and of unwanted signal reflectors is one of the main things that's going to cause us to choose one array design over another. So now let's look at our hub design at 140 gigahertz, having decided, based on the arguments that I've given you, field of view, spatial distribution, also just ease of building the thing. We're building a Mimo hub using a linear array. The challenges are that they're, of course, not as hard as some people think, but IC to package interconnects at high frequencies is not easy. Removing heat from the ICs is a challenge, particularly in interposers where the thermal via performance underneath a power amplifier may not be very good. We have to understand that in addition to the high frequency connections between the IC and the antenna, there's an awful lot of power and control and local oscillator reference and baseband information signals that have to be routed around, and it can be very difficult to fit all of those in. And then most important of all is economies of scale. There are some really truly high performance packaging technologies that work quite well in the multi-hundred gigahertz range, but they're most accessible to high volume players, the folks that make cell phones and laptop computers, and smaller organizations like research labs or universities find it very hard to access these and are forced to use, therefore, lower performance packaging technologies. So in terms of connections between ICs and antennas, you can do a little bit of a MEMS process and etch an antenna structure into the end of an IC and stick it into a waveguide. Northrop Grumman has demonstrated this and works extremely well even at 1 terahertz. Maybe that'll be manufacturable one day, quite possibly will. Ribbon bonding, which is a wide bond for lower inductance, is used by the instrument manufacturers and works quite well up to a couple hundred gigahertz. But the machinery to do this requires skilled operators and is therefore not a production technology outside the instrument business. Gabriel Rebez's group at San Diego puts a quartz substrate, superstrate, directly on top of his silicon ICs, and the superstrate carries patch antennas. And as long as that geometry works for you, that can work quite well. Flip chip technologies, particularly the fine geometry copper studs that are now used a lot in digital packages, also works quite well, even to well above 200 gigahertz, though we do have to worry about the thermal design of getting the heat out of the integrated circuit. Hot vias, meaning vias through the ICs, not only for ground but signal, are another good option. Simple wire bonds are pretty good below 100 gigahertz, but not a good idea above roughly 100 gigahertz. So now let's look at our 140 gigahertz hub design. We're using an indium phosphide power amplifier manufactured by Teledyne Corporation. Puts out about 100 milliwatts and is about 20% efficient. There's a LTCC ceramic module here where the antennas, the indium phosphide power amplifiers go here. This is from Kyocera. And from Global Foundries, there are 22 nanometer silicon integrated insulator CMOS ICs, either transmitter or receivers. This is a transmitter module, so the CMOS ICs go there, the indium phosphide power amplifiers go there. We're using flip chip bonding for the CMOS ICs with copper stud technology. And because of logistics, although it's not a recommended choice, we're using simple wire bonds between the indium phosphide power amplifiers and the ceramic. I'm just showing you here elementary measurements of a CMOS IC interfaced to an antenna. The antenna has about 10, 11 dB gain and about 10 degree beam width in this direction. And of course, in this direction here, it's nearly isotropic. Here's some data transmission experiments with that. Here's a similar package with the CMOS IC and then that indium phosphide power amplifier IC. And of course, that can put out a lot more output power. And again, here are data transmission experiments with that. Now, these are single channel modules. The object is to build a Mimo array. And the Mimo array you would build from smaller units called array tiles with 8 elements. So here I'm showing you, these are actually a mixture of a transceiver, transmitter and receiver Mimo array tiles, but you can see how a larger array would be built from this. And you can see a close-up of this, okay? So the receiver IC is a combination of the ceramic piece with CMOS ICs and the patch antennas, printed circuit boards to provide the low frequency connections and the DC power. Here you see the ceramic piece with the CMOS. The transmitter array is similar, again with an LTCC carrier, the patch antenna array on the ceramic, indium phosphide power amplifiers and CMOS ICs. Here's a photograph of the thing with the indium phosphide and the CMOS. And results are not quite as good as we want, but we have these working now. And these results are currently under review, submitted to a conference, the B6 conference, which will be in December in Monterey. So now let's move up from 210 to 280 gigahertz, from 140 gigahertz up to 210 and 280 gigahertz. I'm going to remind you, without repeating the link budget discussion, that our view of this is our vision here is to do a link demo. We may not be able to do this with a 16-element subarray just because of the amount of hardware we can build, but the intent is to build an 8-element transmit array, an 8-element receive array, and to try to push up the data rate into the several hundred gigabits per second over with a link budget sufficient to support half a kilometer range, even if it's in bad weather and with large safety margins. So here and designed by my ex-PhD student who's now been a professor for a decade or more at Sun Kyung Kwan University, Munkyo Seo, on sabbatical at UCSB and working with my PhD students, designed a 210 gigahertz transmitter and 210 gigahertz receiver in Teledyne quarter micron indium phosphide heterojunction bipolar. These things have a phase shifter so that we can do RF beam steering if we want, but they also have baseband IQ, so we can do MIMO with them. The bandwidth of the transmitter is about 20-25 gigahertz. Output power depends on the exact frequency, but is in the range of 16.5 to 15.5 dBm. Similarly, the receiver has about 20 gigahertz bandwidth. The noise figure, not as good as an indium phosphide FET, but surprisingly good for bipolar technology, is about 7.5 to 9 dB as a function of frequency over the frequency range of interest. So both of these ICs are now working. And we are now working on designing the packages so that we can build these MIMO links. So that's at 210 gigahertz. I just mentioned that in all of these frequency ranges, one of the key components to that is an efficient, moderate to high power output power amplifier. And so all of these were designed by Ahmed in Teledyne quarter micron technology, 140 gigahertz, 130 gigahertz, 194 gigahertz, 266 gigahertz, all with record-setting efficiency and frequency range. I would mention that at Teledyne, Zach Griffith is also setting records of power and efficiency of power amplifiers in this frequency range. We have just taped out, no measurement data yet, no ICs back. We'll have to see if they work. But we've just taped out a similar chipset at 280 gigahertz of a receiver and a transmitter. Here are the students involved in designing that. Again, Munkyo Seo is involved in this. Again, it's in Teledyne quarter micron technology. Receiver in this case simulates at about 11 dB noise figure. The transmitter simulates at about 17 dBm output power. And again, these are from MIMO links. Okay, so now let's just briefly consider the case of two-dimensional arrays for the most difficult case of things like an airborne radar or imaging system where you need to steer over nearly 180 degrees, both vertically and horizontally, and the implications of doing that, okay? So here the packaging challenge becomes much more difficult because suddenly we need to have an element pitch of half a wavelength, which is even if we go up to 0.6 wavelength, which reduces the steering range a bit, it gives us an element pitch of about 1.2 millimeters at 150 gigahertz, a little bit less than 1 millimeters at 200 gigahertz, and so on. So there's not a lot of area to fit in the electronics. In addition, to get a link budget that would be interesting for an aerospace application, the arrays need to be very large. No longer 100 element, but pushing on the order of 1,000 elements or even more. So there are a couple of challenges here. Even if we really simplify the block diagram of the front end ICs of the array, there's a lot of electronics that has to fit within that half wavelength by half wavelength pitch. One end run is to move from a classic tiled architecture like this to a classic trade architecture like this, also known as a slat architecture, because now, although you still need a half wavelength this way and a half wavelength that way, you've got more space in this direction, albeit in a technology that's more expensive to manufacture and physically less compact. So there's, particularly in the tiled architecture, which is physically more attractive, there's not only the issue of fitting all the electronics in, there's also the high thermal density, and there's a large number of signal lines that need to be routed under the IC. So there are challenges in what packaging technology goes underneath the ICs, both to provide a lot of high quality, high frequency signal connections to the ICs, but also low vertical thermal resistance to get heat out of the integrated circuit. So these are the challenges. Just a comment here to suggest that it may not all be doom and gloom. If we look at the Fritz's transmission formula, look at the received power as a function of the transmit power, and write the antenna gains in terms of not directivities, but aperture areas, then, of course, as is well known, in this case, if we keep the aperture areas constant as we increase the frequency, then the ratio of receive power to transmit power improves, gets better as we go up in frequency instead of getting worse, as long as the atmospheric attenuation stays the same. Well, if you look at worst case atmospheric attenuation between roughly 250 and 50 gigahertz and 250 gigahertz, it doesn't vary that much under worst case conditions. And so, in fact, things might look a little bit better at higher frequencies. Since that received power sets our communication rate, what it ends up implying is that the number of beams we radiate times the bit rate per beam, the overall communication capacity, can end up increasing. Specifically, if we choose a scaling strategy as follows, we've got an array at 100 gigahertz, we say, fine, let's replace that one at 200 gigahertz. And let's make the following decisions. Let's keep the overall area the same. And let's keep the radiated power the same. From this, we find that we've quadrupled the informational communication capacity of the array, and yet the output power per unit area has stayed the same. So we have 4 times as many transmitters, and each transmitter is 4 times as smaller, but each transmitter is outputting 1/4 the output power. So the power per area of the IC has stayed the same. Furthermore, a lower power amplifier has smaller die area. So these things suggest that in a tiled array, we may be able to pull this off even at 200 gigahertz, and certainly in a trade array. So the overall trends there depend terribly on things like the atmospheric attenuation, but if we follow scaling strategies in this fashion, it may be possible to build effective two-dimensional arrays even at 200 to 250 gigahertz. So now to return again to the original focus of my talk, I've been talking about 100 to 300 gigahertz wireless. Why consider this? Because you can get massive capacities for a couple of reasons. One is because there are large available bandwidths, and that increases your capacity, but also because the wavelength is short. An array of a given size has more elements, and if it has more elements, given the right signal processing behind it, you can support more simultaneous independent beams, whether it's a base station talking to many users or a point-to-point link with multiple beams between the two endpoints. These systems inherently are very short range, in the range of 100 to maybe 100 meters to maybe half a kilometer. And partly this is simply the short wavelength, the lambda squared over r squared term. And partly it's the high foul weather or even good weather, but humid, high atmospheric losses. And we've got easily blocked beams. We've got to contend with that with some kind of mesh network. The IC technology for these systems will be all silicon if the range is very short and if the signal frequency is well below 200 gigahertz. As we start to go to longer ranges, say at 140 gigahertz, we start to look at either SiGe or 3.5 power amplifiers, and we start to look at maybe 3.5 low noise amplifiers if we want to increase the range. Sounds scary, but that's the cell phone technology today, uses a gallium arsenide power amplifier. And if we want to go up to frequencies significantly above 200 gigahertz, we're going to need to use SiGe or indium phosphide just to build the high frequency portions of the signal chain. So what are the major challenges? The major challenges are the computational complexity of the backhead and digital beamforming. As I say, not at this conference, but at the European DRC and SSIC, the IC and Semiconductor Conference that's running concurrently with this one, Christoph Studer will be showing a phenomenal new result in high efficiency, high throughput, low power digital beamforming ICs. The other challenge is in packaging, fitting lots of signal channels into very small areas. In some form of mesh network or alternative propagation paths to accommodate beam blockage. And finally, I need to emphasize that all of these link budgets with multi-terabit aggregate capacities, even with output powers and noise figures consistent with today's technology, how can that work? And the answer is because I'm postulating systems with something of order 100 transmit and receive array channels. To make these things practical, we need to drive not only the digital beamformer, but also the RF front-end and module technology down to low cost per channel. So that concludes my presentation, perhaps a little bit quicker than I planned, but I will move back to the session chair for questions, and thank you for your attention. So thank you very much.
Thank you, Mark, a lot for this very comprehensive and interesting talk. And we have now time for questions, and please raise your questions in the chat window of this session. And I noticed that there is already one that appeared during the session, so I will read that aloud. And then Mark already answered to that, but I let him to rephrase his kind answer to that. And during that time, I let everybody else to set any questions you might have. So the first question is, may you talk about other aspects of PHY, for example, modulation, coding, synchronization, ADCs, and DACs? So Mark, please.
So some of the questions were partly answered as the talk went on, but the questions are, what about all of the signal processing? And one of the key things to understand is the expectation when you get started with massive MIMO is, oh my goodness, I've got all of these signals that are going to cross interfere and cross modulate if I have non-linearities, if I have phase noise, if I have lower A to D resolution. Oh my gosh, it's never going to work. But say, hang on, let's look at this more carefully. Even under an extreme load factor, the load factor is the ratio of the number of people you're talking to the number of RF channels you have. And we're looking at an extreme case of a load factor of 50%. Many other people are looking at lower load factors. So you've got more RF channels than the number of signals you're dealing with. That is effectively a form of oversampling. And that relaxes the hardware specifications on each channel. So what we find in the team, meaning my collaborators in the center with the systems people, are, for example, for QPSK at a load factor of 50%, you only need, if you've got power leveling, about 3 bits of resolution in your A to D converters. And you just need to increase that to accommodate whatever level of power leveling you may need. Phase noise requirements, for similar reasons, it seems scary, but in fact, the phase noise you need in a massive MIMO system is slightly relaxed compared to the phase noise in a single beam system if you've got the same symbol rate, the same carrier frequency, and the same constellation. 1 dB gain compression points, detailed analysis, similar underlying principles is that the 1 dB gain compression points in the RF signal chain need to be about 5 dB above the average power levels. So those are the points that I understand well and I can address. I think there was some questions about the PHY and things which are beyond my understanding. Oh, what modulation format do we want to use? And that's not clear we've been looking mostly at QPSK because your signal to noise ratio is kind of low. QPSK is clearly very attractive. You presume that you've got a lot of bandwidth available because you're high in frequencies and you're using massive MIMO to get a lot of bits per hertz. But ultimately, that depends on what bandwidth that the various national governments will allocate to these services, and that'll control the kind of constellations we use. So I hope that's answered that excellent question. Thank you.
Thank you very much. And there is the next one. So what about frequency selectivity and coherence bandwidth? Can you ignore that by simply always assume and utilize line of sight?
I think the terms being used are specialized to a particular field in signal processing, and I'm not sure I understand them. Frequency selectivity, meaning if you're just trying to separate one frequency band from another, of course, what we do is use filters. And of course, at the baseband and at the IF, we can build very, very sharp filters. So it's more an issue of sort of cross modulation due to IP3 nonlinearities in the front end. And I think for adjacent channel interference, what we do is we will probably put fairly sharply selective filters in the connection between the transmission line and between the antenna and the integrated circuit, if that makes sense. On the issue of coherence bandwidth, I guess I don't know the terminology, but I don't believe we have a problem there in terms of carrier synchronization. I mean, you do things like differential encoding to deal with low frequency phase noise issues. So perhaps that answers the question. Okay. Thank you again.
Yes, thank you. And I have 1 more minute for others to make new questions, but I have one of myself, because we've been discussing over the years a lot that what are the right technologies, and in cellular domain we've seen all the time that CMOS and to a certain extent now the silicon germanium BiCMOS as well is kind of the choice of the technology, and you're proposing at least to high frequencies, really 3 to 5 finally to come. So what's your prognosis of the timeline and in a way development of the cost in those challenging technologies in terms of market? So how you see, how long will it take that they are really cost effective, and is it really about the market volume, or is it about the advancement in technologies in per se?
So it's an excellent question. First off, in terms of performance, everything's a moving target, but today, again, CMOS is pretty good up to about 150 gigahertz. In fact, it beats SiGe both on noise and output power and efficiency at 150 gigahertz. By the time you get to 200, the roles are reversed. The 3.5s are consistently outperforming silicon in any form, and the power added efficiencies of the power amplifiers in particular there's a big advantage. An even bigger advantage is receiver noise. An indium gallium arsenide channel field effect transistor, whatever flavor, is easily 3 dB better noise than anything else you could conceive, and that's a huge advantage. So can you bring these things to manufacturing? And the answer is, with regard to indium phosphide bipolars, it's entirely not a physics question. It's an issue of the chicken and egg problem of, if you get some market, that drives the volumes, that drives up the yield, that drives down the cost, and you can get other markets. It's kind of like the Tesla automobile today exists because of lithium-ion batteries being developed for laptop computers. Otherwise, it would have never happened, right? So unfortunately, I can't answer that question, though I'm really eager to talk to people who would, in manufacturing firms who might be looking at indium phosphide bipolar. Look, it's no more complicated than gas HBT, and that's in everybody's cell phone. So it's clearly possible. It's just an issue of getting that virtuous cycle of manufacturing volumes going. The indium phosphide FETs, what worries me is those 30 nanometer T-gates that you need. I don't know how you make that manufacturable, even if you invest $1 billion. So I think we need some alternative to that T-gate technology if we're going to build the FETs in high volumes for commercial applications. Yeah, that would be my feeling there. Yeah, thanks for the question.
Yeah, thanks a lot. Very, it's a comprehensive answer, and of course, then market will give some answer to us in the next 10 years. So there is one more at least. So in different cellular generations, we have talked a lot about the modulation, multiple access, and so on. So how do you see the viability of multi-carrier and OFDM for millimeter wave bands due to their high peak to average power ratio?
So most of that is beyond my skill set. Again, I'm a transistor and a sort of small scale integrated circuit designer, leading a team of 21 professors, and my colleague Sandeep Rangan would provide the answer. So send me an email and I'll answer that offline. Just my quick comment is I make the following comments that I can do within my expertise is what the system team has found, unsurprisingly, is the propagation environment at the higher frequencies has far fewer non-line of sight paths. And so we're seriously asking the question of, do you even need OFDM-like techniques, or do you simply, you may have one or two non-line of sight paths that are down 8 to 10 dB. Maybe what you do is in your large phased array, you just set the array coefficients to null those out. And then you don't need to deal with intersymbol interference problems. Now that's a speculation. Again, I'm outside my field of expertise, but the question is, do you need OFDM? You know, how long, a grouping of symbols do you need for that, given the delay spreads you're going to see? Or can you just, you're in an environment where there's far fewer scatterers. You have far fewer non-line of sight paths. So where does that change it? So again, I'm speculating on that point. It really needs to go to other people. If you want a good answer, please email me either directly or have Arno email me, and I'll get it to Sandeep Rangan at New York University, who's the person in our center who looks at those things. All right, thank you so much.
Okay, thank you. And I think that the one of the aspects is really that you were also saying that we don't need to have that back off to get more power out and so forth. So that you were referring already in your talk.
Oh, that's absolutely
appropriately.
Correct. Yeah, is we only want to use OFDM if we have to, because limited dynamic range. We want to keep the peak to average power ratio as friendly as we can get it. Yeah.
Yes.
Exactly. Thank you.
Okay, thanks a lot. So I don't have any other questions further, and I think we have had a very nice discussion on different topics during this session. So my privilege and pleasure is now to thank Professor Rodwell for this excellent talk and excellent answers to those questions. So thank you very much.
Thank you, and it's been a pleasure and honor. Thanks so much for inviting me, and I hope to all see you in person someday before too long.
Yes, that's the same for you as well. And thank you, Mark. And this will end our session today. So thank you, everyone listening, and we close now. Bye-bye.